Now in this video we'll understand about Rayleigh-Ritz method. So far we understood about Galerkin method. Galerkin method we can use polynomial solution either linear, quadratic or cubic, right? So let's see how this Rayleigh-Ritz method works. So in this Rayleigh-Ritz method, the governing differential is first converted into the equivalent integral form as in the case of Galerkin method, and then the calculus of variations is used to define an equivalent variation or energy functional. Further, a function that minimizes this energy functional represents a solution of the governing differential equation. Later we must choose a function which minimizes this energy function. We will use the principle of minima here in case of Rayleigh-Ritz method. Right? So here what we are using, variational calculus and Rayleigh-Ritz method. So let's understand. So with the example of deformation of an axial bar. Right? So consider a linear elastic bar of any arbitrary cross section which is subjected to distributed axial load Q of x along the length and concentrated axial load P applied at some locations on the bar. Let the area of cross sections at any x be A of x. So as we have seen in the previous examples, we have considered a bar which is fixed at left end and subject to a load P at the right end and a distributed axial load of Q of x. Now the strain energy can be written as half into integration sigma x epsilon x into dV over the volume. Right? If you simplify this one, half into, you will get half into sigma x epsilon x into A of x. Further, substituting for sigma x equal to E into epsilon. Sigma is equal to E into epsilon. If you substitute, what you will get? E epsilon square A of x in dx. Again, right? Epsilon is equal to du by dx. Substituting for epsilon is equal to du by dx. This is from the knowledge of mechanics of deformed bodies, right? There you might have studied this one. You will get E into du by dx whole square A of x into dx. And then work done by all external applied forces can be obtained as W is equal to 0 to L Q of x into U of x dx plus summation of I is equal to 1 to n summation of I minus 1 to n pi U of x xi. So therefore potential energy of axial deformation is defined as, from the knowledge of this structural analysis there you studied, potential energy is given as the U minus W, right, where U is the strain energy and W is the work done by the external applied forces. Substituting for U and W, so we can get these expressions. So here a function U of x that minimizes the potential energy is considered as a solution of the differential equation, which will govern the axial deformation of the bars. Right? So this is the expression. In this we need to find out a function U of x which minimizes this total expression. Right? Now again we consider the same problem, right? Considering the same problem, a bar subjected to a load P at right end and fixed at left end of length L and the distributed axial load of C of x. And in the previous slide we derived this expression, Rayleigh-Ritz equation, or from the principle of minimum potential energy, right? So again we start by assuming a linear solution, that is linear polynomial U of x is equal to A0 plus A1x as the approximate solution. And essential boundary conditions are at x is equal to 0, x is equal to 0, we will substitute U is equal to 0. Right, at x is equal to 0, U is equal to 0. If you substitute that essential boundary conditions, what you will get? A0 equal to 0, right, in the above solution U of x. Since the admissible solution can be written as U of x is equal to A1x, du by dx is equal to A1, u of L is equal to a1L, right? So this is the admissible solution. And finally, phi is equal to substituting this u of x function in the